Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 3 for our MCAT Physics and Math playlist, and this chapter is titled Thermodynamics. Here we're going to cover 4 main objectives. First, we're going to begin by going over the zeroth law of thermodynamics. In discussing this law, we're also going to dive into the concept of temperature, and we're going to learn how to convert between 3 temperature scales: Celsius, Fahrenheit, and Kelvin. After that, we're going to move on to understanding thermal expansion and how it affects materials. Next, we're going to explore the different types of systems in thermodynamics. We'll distinguish between open, closed, and isolated systems. In addition, we will learn the difference between state versus path functions. In the third objective, we're going to tackle the first law of thermodynamics, focusing on heat transfer, and energy transformation. We're also going to look at the different types of thermodynamic processes, such as isothermal, isobaric, isochoric, and adiabatic processes, to see how systems behave under varying conditions. Then finally, we'll end the chapter by discussing the second law of thermodynamics. In doing so, we're going to explore the concept of entropy, and we're also going to take a closer look at how energy disperses within a system. Now, with that introduction, let's go ahead and get started on that first objective. Temperature. This is one of the most fundamental concepts in thermodynamics. It quantifies the average kinetic energy of the particles within a substance. In essence, temperature gives us a measure of how fast the particles in a substance are moving. At higher temperatures, particles are moving more quickly, while at lower temperatures, their movement slows down. This microscopic behavior translates into the macroscopic effects that we observe, such as heating or cooling of an object. On a larger scale, temperature differences between objects dictate the direction of heat flow. Heat naturally moves from areas of higher temperature to areas of lower temperature, and this process continues until thermal equilibrium is reached, meaning that there is no net heat flow between the objects. In short, heat is the transfer of thermal energy from a hotter object to a cooler one. Now, when 2 objects are in contact, if no further heat flows between them, it means their temperatures are equal and they're said to be in thermal equilibrium. This concept is really important in thermodynamics because it helps us define when systems have reached a balanced state in terms of energy distribution. With that being said, it's going to be important for us to discuss the zeroth law of thermodynamics. This law, it provides the foundation for our understanding of temperature and thermal equilibrium. The zeroth law states that if 2 systems are in thermal equilibrium with a third system, then they must also be in thermal equilibrium with each other. So for example, if block A and block B are in thermal equilibrium, and block B and block C are also in thermal equilibrium, then the zeroth law asserts that block A and block C must also be in thermal equilibrium with each other. Now, this simple yet powerful concept really allows us to define temperature as a measurable property that can be used to determine the state of thermal equilibrium across multiple systems. To quantify temperature now, we can discuss the various scales that have been developed over the centuries. And today, 3 major temperature scales are commonly used, and those are the ones that we're going to go over. They are Celsius, Fahrenheit, and Kelvin. Let's start with the Celsius scale. This is widely used around the world, both for everyday temperature measurements and for scientific work. This scale is based on the properties of water, with 0 degrees Celsius marking the freezing point, and 100 degrees Celsius marking the boiling point. Now we can convert between Celsius and Fahrenheit. If you know your temperature in Fahrenheit, you can convert it to Celsius using this equation right here, where Celsius is equal to 5/9 multiplied by everything in the parentheses. This is Fahrenheit minus 32. Now, in contrast, the Fahrenheit scale, this is most commonly used in the United States for non-scientific purposes. On this scale, water freezes at 32 degrees Fahrenheit, and it boils at 212 degrees Fahrenheit. Although less common outside the United States, understanding the Fahrenheit scale is important, particularly for comparing temperature data from different regions or sources. If you know your temperature in Celsius, you can convert it to Fahrenheit using this equation right here. 9/5 multiplied by Celsius plus 32 gives you your temperature in Fahrenheit. Finally, the Kelvin scale. This is the standard in scientific research, and it is part of the International System of Units. What makes the Kelvin scale unique is that it starts at absolute zero. This is the point at which particles theoretically stop moving altogether. This absolute zero is equivalent to minus 273.15 degrees Celsius. Now, to convert from Kelvin to Celsius, you would want to use this equation right here that says Kelvin is equal to Celsius plus 273.15. Now, with this foundation laid, we can better understand how temperature and heat govern the behavior of systems, allowing us to move on to explore different types of systems in thermodynamics. But before we get there, let's do one practice problem together. This problem says, if a meteorologist says that the temperature will reach a high of 86 degrees Fahrenheit today, what will be the high temperature in degrees Celsius and in Kelvin? Now, to convert from Fahrenheit to Celsius, we're going to use this equation. Celsius is equal to 5/9 multiplied by everything in the parentheses, which is Fahrenheit minus 32. Now we know our temperature in Fahrenheit, so we can go ahead and plug it into our equation. 5/9 multiplied by, in parentheses, 86 minus 32. Now this gives us 5/9 multiplied by 54. Now this multiplication division process can become a little bit easier because 9 and 54 are both divisible by 9. So we're going to divide both of these values by 9. This becomes 1, this becomes 6, and now what we have is just 5 multiplied by 6, and that gives us 30 degrees Celsius. Now, what about converting this to Kelvin, right? We know that our temperature is 86 degrees Fahrenheit. We were able to convert that to Celsius. It's equal to 30 degrees Celsius. What about what this temperature is equivalent to in Kelvin? In order to do that, all we have to do is take our temperature in Celsius and add 273.15 to that value. This is going to give us 303.15 Kelvin. So 86 degrees Fahrenheit is equal to 30 degrees Celsius and equal to 303.15 Kelvin. Wonderful. Now we can discuss the next topic, which involves thermal expansion. This is a key concept in understanding how temperature affects the physical properties of materials. It has been observed that certain physical properties of matter change when the temperature changes. As matter heats up or cools down, properties such as length, volume, solubility, and even the electrical conductivity of materials shift as a function of temperature. This relationship between temperature and material properties plays a key role in the development of the temperature scales that we use today. While we won't dive deeply into the history of how thermometers and temperature scales were developed, it is useful to note a few important points. For instance, the Fahrenheit scale, which is widely used in the United States, it was developed by Daniel Fahrenheit. He created his scale by placing a mercury-filled thermometer into a mixture of ice, water, and ammonium chloride. The height of the mercury column corresponds to specific temperature markers, such as the freezing and boiling point of water, allowing for the consistent measurement of temperature. Once these markers were established, the thermometer could be used to measure the temperature of other objects based on the principles laid out in the Zeroth law of thermodynamics. Now, this principle behind this temperature measurement is thermal expansion. A change in temperature often results in a change in the physical dimensions of a substance. In most solids, for example, a rise in temperature will cause an increase in length, while a drop in temperature will cause a decrease in length. This relationship is governed by this formula right here. Delta L, this is the change in length, is equal to alpha. This is the coefficient of linear expansion, multiplied by L, this is the original length, multiplied by delta T. This is the change in temperature. Now, the coefficient of linear expansion, this is a constant that characterizes how a specific material's length changes as the temperature changes. This usually has a unit of inverse Kelvin, although it may sometimes be quoted as inverse degrees Celsius. This difference really is inconsequential because the unit size for the Kelvin and Celsius scale is the same. In short, this equation tells us that the change in length is proportional to both the initial length of the material and the temperature change it undergoes. And again, the coefficient of linear expansion, this is going to vary between different materials, with metals generally expanding more than nonmetals when heated. Now, the best way to learn how to use this equation is by tackling a practice problem. This problem says a metal rod of length 2 meters has a coefficient of linear expansion of 10 to the minus 6 inverse Kelvin. It is cooled from 1080 degrees Celsius to 80 degrees Celsius. What is the final length of the rod? Now, we're given a lot of information here. We know the coefficient of linear expansion. It's equal to 10 to the minus 6 inverse Kelvin. We're also given the original length, 2 meters, and we're told what our initial and final temperatures are so we can calculate delta T. This is going to be 80 minus 1080. Now that we have all these variables, we can just go ahead and plug it into our expression. Delta L is equal to alpha multiplied by L multiplied by delta T. This is equal to 10 to the minus 6 inverse Kelvin multiplied by 2 meters multiplied by 80 minus 1080. And we're going to use the Kelvin scale here because we want our units to cancel. And when you're taking a difference in temperature, you can easily convert between Celsius to Kelvin because the difference will be the same regardless of using Kelvin or using Celsius. So 80 minus 1080 in degrees Celsius is going to give you the same difference as 80 minus 1080 in Kelvin. So we're just going to use Kelvin here because our coefficient of linear expansion is in units of inverse Kelvin. And that way, our units cancel out. And what we get is minus 2 times 10 to the negative 3 meters. Now, the negative sign here represents a decrease in length. The original length was 2 meters. Therefore, the final length is going to be 2 meters minus 2 times 10 to the negative 3 meters. And that gives us our final answer of 1.998 meters. And that's our final answer. The final length of the rod is 1.998 meters. Now we can discuss our next topic, which involves liquids. Liquids experience a slightly different form of expansion. Since liquids don't have a fixed shape like solids, their volume is the primary property that expands when heated. In liquids, the only meaningful parameter of expansion is volumetric expansion, which is given by this formula right here. Delta V is the change in volume, B is the coefficient of volumetric expansion, V is the original volume, and delta T here is the change in temperature. Now, the coefficient of volumetric expansion, this is a constant that characterizes how a specific material's volume changes as the temperature changes. Its value is equal to 3 times the coefficient of linear expansion for the same material. So again, I want to reiterate that. Similar to solids, the coefficient of volumetric expansion depends on the specific properties of the liquid being heated. And this concept applies to both liquids and solids, though in the case of solids, we typically focus on linear expansion rather than volumetric expansion. Now, to understand how to use this equation, let's tackle a practice problem. This problem says, suppose that a thermometer with 1 milliliter of mercury is taken from a freezer with a temperature of negative 25 degrees Celsius and placed near an oven at 275 degrees Celsius. If the coefficient of volume expansion of mercury is 1.8 times 10 to the negative 4 inverse Kelvin, by how much will the liquid expand? Now we're given a lot of useful information. First, the coefficient of volumetric expansion for mercury is equal to 1.8 times 10 to the negative 4 inverse Kelvin. We're also told that the original volume is equal to 1 milliliter. And finally, we're given the initial and final temperature so we can calculate change in temperature. Our final temperature is 275 degrees Celsius, and this is minus our initial temperature, which is negative 25 degrees Celsius. Now, when we do this, we get a change in temperature that is equal to 300 degrees Celsius. This is also equivalent to 300 degrees Kelvin. We don't need to convert our Celsius to calculate change in temperature and have it in units of Kelvin. And the reason we want it in units of Kelvin to begin with is because our units for the coefficient of volumetric expansion is in inverse Kelvin, and we want those units to properly cancel out. But again, the reason why we don't need to convert our temperature from degrees Celsius to Kelvin to calculate change in temperature is because both scales have the same magnitude of scale. That means if you have temperatures in Celsius and you were to convert them to Kelvin and then take the difference, you would obtain the same value as if you had taken the difference directly in Celsius. And this is because the offset between Celsius and Kelvin cancels out when you're calculating the difference, leaving the same numerical value for the temperature change. This is the same reason why we didn't convert Celsius to Kelvin in the previous problem when we were calculating the final length of the rod. In the MCAT, you have limited time to tackle these problems. So information like that is really useful to save you time. When you're taking change in temperature, whether you have it in Celsius or Kelvin, go ahead and just calculate the difference in that scale. And that delta T that you calculate, it will have the same value on the Celsius scale as it would in the Kelvin scale. Now that we have all three of these quantities, we can go ahead and plug them into our equation to calculate how much the liquid will expand. The change in volume is going to be equal to 1.8 times 10 to the negative 4 inverse Kelvin multiplied by 1 milliliter multiplied by 300 Kelvin. This is going to give us an answer of 0.054 milliliters. So how much will the liquid expand? It will expand by 0.054 milliliters. Wonderful. Now we can move on to objective 2. In thermodynamics, it's crucial to understand the distinction between the system and the surroundings. When analyzing any reaction or process, we divide the universe into the system and the surroundings. The system refers to the specific part of the universe that we're focusing on, which could be a chemical reaction, a sample of gas, or any defined quantity of matter. The surroundings, on the other hand, include everything else outside of the system. This can be the container, the room, or even the larger environment where the system exists. For example, if we're analyzing a chemical reaction, we can define the system as the reactants and products involved in the reaction, and then we can define the surroundings as everything else, including the reaction container, the air in the room, or anything external to the chemical reaction itself. Now, in defining the system and the surroundings, it's also essential to consider the boundary that separates this system from its surroundings. The nature of this boundary determines how energy and matter are exchanged between the system and its surroundings. Based on this interaction, we can classify systems into 3 main categories: isolated, closed, and open systems. Let's start with isolated systems. These systems are completely insulated from their surroundings. They cannot exchange energy or matter with their surroundings. An example of an isolated system would be a bomb calorimeter, which we discuss in detail in the MCAT General Chemistry playlist. It's designed essentially to prevent any exchange with the outside environment. A closed system. In this type of system, energy can be exchanged with the surroundings, but matter cannot. A good example of a closed system is a steam radiator where heat is transferred to the surroundings, but the water, the matter, stays within the system. Last, we want to discuss open systems. These systems, they can exchange both energy and matter with the surroundings. An example of this would be a pot of boiling water where heat is transferred to the surroundings and water in the form of steam escapes into the environment. Now that we've explored the different types of systems, it's also important to understand a key concept in thermodynamics, and that is a state function. A state function is a property of the system that depends only on the current state of the system and not on how that state was achieved. In other words, a state function is independent of the path taken to reach that state. Examples of state functions include temperature, pressure, volume, energy, and enthalpy, which we'll discuss later. These properties, again, depend only on the initial and final states of the system and not on the process that leads from one state to another. On the other hand, heat and work, these are not state functions. They're referred to as path functions because they depend on the specific process or path taken to transition from that initial to that final state. In other words, heat and work describe the energy transfer along the path rather than the state of the system at a given moment. To clarify, heat and work are involved in the process of change, but they do not define the system's equilibrium states. They describe how energy is exchanged as the system moves from one state to another. Therefore, they're not part of the system state at the start or the end of the process. That's why they're not classified as state functions. So in summary, state functions give us a way to define the equilibrium properties of a system, while path functions like heat and work help us understand the processes that lead to those equilibrium states. Now, with that, we've covered objective 2, and we can move into objective 3, which we'll actually cover in the next video. So I hope this has been helpful so far. Please let me know if you have any questions, comments, concerns. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.